Perfect. So hello, everyone. Welcome to the next iteration of our strings seminar. So it's a great pleasure to introduce today's speaker, Seung-Joo from IBS Daejeon. Seung-Joo has a PhD from Oxford, as far as I know, and has done postdoc positions at Kias, Virginia Tech, and CERN before returning to Korea recently. And he has also been a plenary speaker at Strings this year. And his talk today is going to be about tensionless strings and the Swampland.
Okay, thank you very much. So yeah, I'd first like to thank the organizers for kindly inviting me to speak, and in particular, Johanna. In fact, I've never visited the Southern Hemisphere, not even virtually. So I'm even more grateful that I was given this opportunity to at least virtually visit the ANZ area. So thank you so much. The story I'll be telling you today is based on several projects I've worked on in collaboration with my wonderful collaborators, Daniel Klauer at Hamburg, Wolfgang Lehe and Gulli Lokart at CERN, and Timo Weigand also at Hamburg, and Max Wiesner at Harvard. Now, before actually getting to the physics, I'd have to start with a couple of apologetic remarks. I was told that the talk has to be informal and basic, and only little knowledge about string theory is to be assumed. So accordingly, I plan not to delve too much into technical details of string theory. So the string experts in the audience may find the talk too colloquial, but hopefully some of the results I'll be reporting are not too trivial even to the experts. And in the same vein, I will focus mainly on this 2-year-old paper, because I thought this work would nicely deliver the flavor of the general program I've been pursuing without getting too much into the technical details. However, at the end of the talk, in the outlook part, I will briefly introduce more recent results and also this work in progress with Timo and his student Raphael. And I'll try to put these more recent works into the context of this talk. So the motivation starts from the notion of the landscape. So at very high energy, we have a UV complete quantum gravity, which for the purpose of this talk will be a string theory. And this is a very much constrained theory. It's almost a single point in the theory space up there. But once you flow down into the low energy regimes, this unique theory leads to a vast set of EFTs known as the landscape. And the idea here is that the single UV theory has lots of vacua as manifested by a plethora of possible internal geometries. And for each of them, a different low energy physics would arise. So by construction, every theory lying in this low energy landscape has a UV completion into quantum gravity, here string theory. On the other hand, it turns out that there are many apparently consistent low energy QFTs, which nevertheless cannot be completed into quantum gravity. And the set of those incomplete theories is known as the Swampland. Now, such a division of the theory space would not be too useful unless we could come up with concrete practical criteria by which theories in the landscape can be distinguished from those in the Swampland. And in this context, quantum gravity conjectures refer to any consistency constraints on the theories in the landscape that quantum gravity is believed to impose on general grounds. Due to their conjectural nature, however, the validity of each such constraint is very debatable. Let's say we forget about this important debate for now. Then, for a given low energy theory, we can test if it obeys the consistency constraints. And if it fails any of these constraints, we may just dump the theory into the Swampland. So one of the major goals of the so-called Swampland program is then to better understand such consistency constraints and thereby revealing the mysterious nature of quantum gravity In fact, I'd like to emphasize that this is not only for academic curiosity. On the very contrary, this is the kind of program that can, in principle, serve as an intellectual guidance for possible new physics. The reason is simply that the theory of our universe must sit in the landscape. Any innocent new physics ideas, which nonetheless contradict any of the quantum gravity conjectures, should never work. Because if they did work, then our universe would be put into the swampland. And this is the sense in which the Swampland program connects in principle to our universe as a quantum gravity theory. So enough about the abstract definitions. For concreteness, let me now present a few example conjectures. The first example I brought here is the so-called weak gravity conjecture. This conjecture concerns a theory of gravity and electromagnetism, whose couplings are written in this action. And the claim is that there must exist a charged particle in the spectrum with a mass smaller than a charge. And to be precise, the charge to mass ratio of this particle should be bigger than that of the extreme black hole, which I'll denote by μx. And this number is an order 1 constant determined by the theory, the effective theory. And such a particle with mass smaller than charge we'll refer to as a weak gravity particle. In fact, this original form of the conjecture was later on very much strengthened to this much bolder claim that the theory needs to be supplemented not just with one such particle, but actually with an infinite tower of weak gravity particles. Moreover, an even stronger version further claims that the tower is not random, but should in fact fill up a sublattice of the full charge lattice. And here the tower scale M0 is naturally expected to sit at the M Planck times the electric coupling G. So the claim is that the spectrum contains the weak gravity particles at mass M0, 2M0, 3M0, and so on and so forth. It is a tower which really becomes infinite if you crank the gauge coupling G down to 0, because the tower scale is proportional to the gauge coupling G. Really precisely at this weak gauge coupling that the conjecture would become more interesting and useful, because a new physics would be suggested at low energy, the tower itself. So partly for this reason, when addressing the weak gravity conjecture later in this talk, I will mostly focus on the weak coupling regime. Now, why do we believe in such a strong claim? Of course, it's been supported strongly in the string theory context, but the original motivation, I must say, in fact, came from a general quantum gravity intuition without relying at all on string theory. So this intuition is the following. The black holes, including...
Yes. Can I ask a very naive question about this?
Yes, please.
So in this analysis, you take into account the renormalization of the gauge coupling? It depends on the...
Yeah, so this is the gauge coupling at a a given energy scale where I'm considering the landscape.
I see, okay, thank you.
Yeah, so this is really the measured gauge coupling. Okay, so so about the quantum gravity intuition of the weak gravity conjecture. So we consider black holes, and the intuition is that black holes and also extreme black holes must eventually decay by emitting a particle. Then one can easily deduce that the emitted particle must be a weak gravity particle obeying this inequality. I won't go through the algebra here, it's just algebras, but just to point out a source of potential debate. In fact, it's not completely clear if the starting assumption that extreme black holes must decay is really kosher. And this part remains as heuristics, and therefore the weak gravity conjecture is still a conjecture. The second example is the so-called distance conjecture. Given a quantum gravity theory with a scalar field, we consider traversing an infinite distance in the moduli space. In other words, we consider deforming the effective theory a lot towards the boundary regime of the effective 3-parameter space. Then the claim is that an infinite tower of states should become light upon such an infinite deformation, in fact, in this exponential fashion. And even stronger claim is that this alpha in the exponent has to be an order 1 constant. Now, again, this claim has been confirmed in many string theoretic EFTs. So I've only just mentioned a couple of examples for quantum gravity conjectures, but there are a lot of conjectures in the literature. And interestingly, it is being found constantly that all of this is rather closely connected, forming an intricate web of conjectures. But in this talk, I won't discuss all of this. Instead, I will just focus on the examples that I've already introduced, the weak gravity conjectures and the distance conjecture. And arguably, they sit at the heart of this web. And in addressing them, I will be invoking the emergent string conjecture, of which precise claim I will state shortly.
I have one question about this,
yes, please.
Picture. So the arrows you're pointing here, can someone say that, does this mean one conjecture implies the other, or is compatible with the other, or is there some sort of a hierarchy of conjectures?
I just meant the indication of the one conjecture indicating the other. Yeah.
Are there backwards arrows as well, or is this like?
Yeah, sometimes. I mean, I'm being very schematic here.
Okay.
Maybe
I'm just
shouldn't have brought this, but yeah, some conjectures may have both directions, but there are some assumptions in making this arrow in any case, so it's not like they're really equivalent. But okay, yeah, it's very sort of dodgy picture. But I just wanted to say that there are some relationships.
Thank you.
Yeah, thanks. So yes, so then the goal of this talk is to verify these conjectures in Kahler for a whole class of string EFTs in a model independent fashion, and to also propose a universal microscopic origin of the conjectured constraints. To be more concrete, our arena will be 4-dimensional EFTs with minimal supersymmetry obtained by string compactifications, with the precise setup being the so-called F theory. And here are the main messages I will try to convey in this context. Firstly, strong evidence is found for the emergent string conjecture, of which claim is the following. At infinite distance in the moduli space of quantum gravity, either the theory decompactifies or a unique tensionless critical string emerges. Essentially, we will confirm this asymptotic behavior of the EFTs for all limits in the so-called Kahler moduli. And these are the EFT parameters that govern the size of the internal compact dimensions of the higher dimensional string theory in terms of the geometry. So the first case, the decompactification, may feel a bit boring, just corresponds to an infinite expansion of the internal space. We are controlling the size of the internal space in any case. So there must be some decompactification limit. And this first case, in the context of the Kahler moduli deformations, may be thought of as being very boring. But this latter case is realized in a much more non-trivial fashion, and we will see how this is realized. In fact, I will address that this emergent light string serves as the microscopic origin of both the distance and the weak gravity conjectures. So these are the main messages, and this way we will actually have solidified the foundations for these conjectures, both from the mathematical and from the physical point of view. On one hand, we provide a geometric classification of infinite distance limits in the Kahler moduli space. And on the other hand, we clarify the physical nature of the light states that fulfill the conjectures. So that's the end of my very long introduction. Have in particular introduced these two example conjectures. Now, the rest of the talk will consist of two parts, addressing these two conjectures in turn, actually. So in part one, a general analysis will be given of the EFTs at infinite distance in the parameter space to address the distance conjecture. Then in part 2, we will use the result of part 1 to analyze the EFTs in the weak gauge coupling limits. And these limits can be viewed as infinite distance limits of a particular kind. And this way we will address the weak gravity conjectures at weak coupling. I will then conclude with the summary and outlook. So let's now proceed to part 1, unless there are any further questions. Okay, good. In part 1, we will be studying the EFTs at infinite distance, and we will explain how the distance conjecture is realized. So let's start with the classical analysis. As already mentioned, the arena is 4-dimensional n equals 1 EFTs of F theory. This is another name for type 2B string theory, compactified on an internal 6-dimensional space X6 in presence of 7 branes that wrap around an internal 4-dimensional cycle, which I'll denote by S. So from the effective field theory perspective, these branes will fill the entire 4-dimensional external space-time and give rise to gauge fields propagating there. On the other hand, from the internal point of view, these branes source a non-trivial axial dilaton profile, and this can be described by endowing the internal space X6 with a certain mathematical structure known as an elliptic fibration. And this amounts to just continuously fibering 2 tori of varying shapes along the internal space X6. But I don't mean to bother you with this fibration geometry today. Instead, I will mostly use the language of type 2B string theory in a 6-dimensional internal space. We can also turn on gauge fluxes, but this won't affect us very much. Now, we will be much interested in the interplay between the gravitational and the gauge dynamics, especially in addressing the weak gravity conjectures later in part 2. In terms of the internal geometry, their couplings are determined by the volumes of the entire internal space X6 and the 4-dimensional cycle S4 therein. And therefore, the moduli space in scrutiny will be the Kahler moduli space of X6. So each point in this moduli space corresponds to a specific Kahler form, which is roughly a metric. So depending on where we are sitting in this Kahler moduli space, the cycle volumes, the collivies here and there, they will vary. Then that's because they are measured with respect to a metric, which is fixed at a fixed position in this moduli space. So specifically, in the expansion of the Kahler form colli J into some fixed basis, we have these so-called Kahler parameters tau i's, and these guys are essentially the 2 cycle volumes. Once we integrate this in this form over 2 cycles, we get the volume of the 2 cycles. And their squares are the 4 cycle volumes, and their cube is going to give us the entire X6 volume. Now, we'd like to classify the kind of physics that can happen at infinite distance in this moduli space. That is, in the space of these tau parameters. To this end, we will first classify the geometry at infinite distance in which one or more of these tau parameters are taken to infinity. Then generically, the X6 volume would also diverge because it's essentially the cube of the taus. And we can write the volume of X6 like this, where mu is a very large parameter. But we can perform an overall rescaling of the Kahler parameters, the tau i's, to these blue ti's, so that the X6 volume measured with respect to this new ruler is going to be finite. So essentially, mu to the -1 observe the infinity in Vx6. So now the simplest case arises when all these rescaled ti's are finite. This amounts to just a homogeneous decompactification. because it's all about just an overall scaling. Obviously, a light KK tower arises in this case. In general, however, such an overall scaling can be accompanied by a relative scaling. This is a residual limit where some of these also TIs are large. Then necessarily some other TIs are to be small because the rescaled X6 volume must be finite by construction. So we are bound to have some shrinking two-dimensional cycles. And for an intuition, you can just imagine stretching one side of a rectangle while keeping the area of the rectangle fixed. Actually, we classified the allowed parametric forms of these rescaled parameters TIs, thereby determining the full geometry for each infinite distance limit. And now I will summarize the characteristic features of this geometric classification.
Sorry, may I ask again?
Oh, yes, please. Yeah.
So you were saying the gauge theories are 4D unequal 1? Yes. I see. So, but you have a number of Carroll multiplets?
Sure, yeah.
And the masses corresponds to the scalar parameters? Is it so?
The scalar parameters are some moduli.
Yeah. So in terms of the gauge theory, which parameter they correspond to?
Oh, they are, in terms of this gauge theory, they are just some chargeless fields, scalar fields.
Oh, I
so
see.
In the EFT, yeah, and we just give some waves to this moduli.
Then, scalar fields.
Yeah.
Okay, I see. I see. So you're okay. I see.
Yeah.
Okay, I see very well. Thank you.
Yeah, sure. Okay.
Can I also ask a few very basic questions?
No, please.
So when you say the Kahler moduli space, do you mean a Kahler cone where you have like a large volume point, or do you mean the stringy Kahler moduli space where, I don't know, can the TIs also go to minus infinity so that you can sort of leave?
No, I'm only considering the Kahler cone. So it's really for the geometry. Yeah.
Okay, and so do these sort of infinite distance point also include, like in the type 2B differential equation language, like are these MUM points, so maximally unipotent monodromy, or can you also?
That's one example. That is one example of infinite distance limit, but there are also other limits.
Right.
Yeah, so I'm considering
and your discussion also contains other infinite distance points.
Yeah. So what I'm going to present is actually the full classification of infinite distance limits.
Okay, fantastic.
And one of which is the type you just mentioned. Yes. Yeah. Okay. So yeah, now I will show you the classification result. So as it turns out, the geometries of the internal X6 in any limits should fall into one of these three classes. So as already explained, the limits involving a relative scaling should have shrinking two cycle. In general, there can be several two cycles that simultaneously shrink, but for some limits, we have actually a unique two cycle that shrinks at a fastest parametric rate. And I will denote such a fastest shrinking two cycle as C0. In fact, C0 turns out to be either a sphere or a torus fiber within X6, and that's how we define limits of class 1 and 2. And to be complete, class 3 is defined to collect all other limits where, by definition, we do not have a unique fastest shrinking two cycle. And the meaning of this drawing is going to be explained shortly. So that was a very quick summary. Let me now go a little more specific. So a little bit of equations. Recall that the metric in a generic limit involved scalings of two kinds. So we first scaled the metric Kali J with an overall large parameter, the red mu here. And this way we defined a rescaled metric, the bold J here. Okay, I didn't use bold J before, but we can rescale this metric to define a rescaled metric. We next considered a potential relative scaling within this rescaled metric. And for this, we need another large parameter, which I'll denote by the blue lambda. So this bold J is a function of blue lambda. And in fact, our detailed classification determines the allowed parametric forms of these tau parameters in terms of these mu and lambda. But rather than giving you all these details, let me just show you some of the resulting volume behaviors like this for class 1 and 2 limits. Firstly, the volume of the smallest 2 cycle, the C0, is of order mu over lambda square. And secondly, the smallest 4 cycle volume is of order mu square over lambda. And the largest 4 cycle expands at mu square lambda square, and the entire X6 has the volume of order mu square, sorry, mu cube. And these volume behaviors will play a crucial role for physics, and I'll refer back to this table whenever needed later. So let's now get to the physics of these 3 classes in turn. For the sake of time, I will just report the results of this analysis, and the details can be found in this paper. Okay, so class 1 limits first. The shrinking 2 cycle C0 can be wrapped by the D3 brane of the type 2B string theory. And this way, we obtain an effective string in the 4-dimensional EFT. Then because the C0 is a sphere fiber in class 1, as I claimed, due to this topological configuration of the embedding of C0 into X6, the resulting 4-dimensional string turns out to be a critical heterotic string. Now, stretching the 3 brane, of course, costs energy. So the tension of this effective string is given by the volume of C0, which is wrapped by the D3 brane. And this is computed as 1 over mu square lambda square in Planck unit. We therefore obtain an emergent tensionless critical string. But this tension better be compared now with the KK scale governed by the largest cycle in the geometry. And this turns out to scale as 1 over mu to the 4 lambda. So within class 1, there arise these 3 qualitatively distinct situations. The physics depends on the way we approach the limit, that is, where we are sitting in this mu lambda space. So in the first regime, the string scale is parametrically bigger than the KK scale. And this indicates a decompactification signaled by the light tower of KK modes. So KK tower is the leading tower. On the other hand, in the second regime, we have the string scale parametrically locked with the KK scale. In fact, if you think about it, this is the familiar situation in string compactifications with the side of the internal space bigger than the string length, but actually not parametrically bigger. The low energy theory in such a limit does not decompactify. And although we started from type 2B string theory, the relevant fundamental string is now this emergent heterotic string, because this heterotic string is much, much lighter than the type 2B. And finally, this last regime looks very strange. This would correspond to a pathological phase of the theory, because the string is much lighter than the KK. This indicates that it's a genuinely defined critical 4-dimensional string, because KK tower is completely decoupled. And this is not expected on general grounds if we believe in string theory. And I will say more about this later. In the same vein, we can also characterize class 2 limits. Now, the shrinking 2 torus fiber leads to an emergent type 2 string rather than emergent heterotic. But the analysis goes really the same way. I won't discuss this class further. And finally, class 3 collects all other limits. The geometric analysis is actually most involved for this class, but the end results lead to this following simple physics. So it turns out that the KK modes always provide the leading lightest tower. So we end up facing a relatively boring situation, and the picture was meant to indicate this physics. So the theory in a class 3 limit just decompactifies, and a simplest limit of class 3 is the homogeneous decompactification to 10 dimensions, full 10 dimensions. There's no relative scaling in this case, just homogeneous decompactification due to the large mu. But there are also more complicated limits of class 3, in which several true cycles shrink together at the same fastest rate. And naively, this looks pathological because then several critical string species would arise, and this would in turn lead to several graviton spaces, to say the least. However, upon going through a careful analysis of the geometry, as I declared, we can prove that the KK scale always wins against the string scale in such a situation. So it's actually a decompactification in disguise. In fact, I should have stressed a related feature of class 1 and 2 limits. There, I just said that the fastest shrinking curve C0 is unique. And thanks to this geometric uniqueness in those classes, we have a unique species of most tensionless critical string there. And that's why the emergent string phase there was consistently defined. In any case, for class 3 limits, in these both situations, we observed that the FTD compactifies as witnessed by a light KK tower. Good. Now, to complete the story, I will briefly comment on our quantum analysis, and will in particular discuss the fate of this pathological regime that we just bypassed earlier. Recall that for class 1 limits, we had this this bad situation where the heterotic string scale set far below the Kaluza-Klein scale. And what I'll address now is that such limits are eventually obstructed by quantum effects. To this end, let's first note that we naturally expect corrections in general because certain cycles shrink in the limits. The first type to consider is perturbative alpha prime corrections. For the experts in the audience, these corrections can be computed via the duality with M theory, but I won't discuss details here. In the end, the Kahler potential is corrected in the manner reflecting the correction to the classical volume of the entire X6 space. And also the natural coordinates describing the 4 cycle volumes are promoted to quantum volumes. And there are formulas in the literature for these corrections. And by applying these formulas to our limits, which we classified, we eventually learned that the leading corrections scale as lambda over mu square. So let me remind you that the large parameters mu and lambda describe the overall and the relative scalings of the metric, respectively. Now, sitting in this pathological-looking third regime, then the perturbative control is obviously lost at alpha prime square order because this lambda over mu square would be very large. The corrections, therefore, exclude such pathological limits, which is nice. So it's not like I'm giving a very, very quantitative analysis to rule this out, but I just already conclude from this parametric computation that these limits are to be quantumly obstructed. So let me remind you that the large parameters mu and lambda, we could put them into any 3 regimes. And we just discussed this third pathological looking regime, and we just said, okay, they are quantumly obstructed. But what about these 2 other regimes? Can we say something about them in the quantum sense? So in this first regime, the corrections are obviously now suppressed because now lambda over mu square is going to 0 in the limit. So the previous classical interpretation just remains valid there. However, this second regime, this is much trickier because the corrections are not parametrically suppressed. And at a very technical level, they depend crucially on the detailed parametric forms of the tau i's, which will in turn determine the numerical coefficients for these alpha prime corrections. And therefore, depending on such precise details, we might as well end up with the same problem as in the third situation. But also, we could easily engineer control situations where the corrections are, in fact, numerically suppressed at least. And this is just to emphasize that there do exist unobstructed limits in this second regime as well. And this exhibits an emergent light string. Okay. Similar results arise also for the
very naive
yes,
question.
yes, please.
I mean, all this analysis is first orders in alpha prime, right? So
yeah, this is the leading order alpha prime. Yes.
But I mean, the results that you're that you're talking about, yeah, they could be very well modified by higher orders.
Yeah, they could be. So that's right.
Is there any way to get exact results in some limits, or because I mean, you state that there are abstractions, but all of this relies on the second order in a perturbative series that might not be. I mean, it might be an asymptotic series, and you're essentially stating that there are high order corrections, but you're only truncating at the second order. So I was just.
That's right. So yeah, so indeed, here I'm only discussing the leading corrections because that's essentially. Okay, we also computed a little bit of the next leading order corrections, but we of course do not compute everything. And what I'm saying is that just by looking at the leading correction, then by observing that the leading correction already diverges, we could just say that this limit is obstructed. So this is just to rule out this obviously obstructed regime. And you know, and we just check the next to leading order corrections, and just find that in these regimes we can make sure that at least the next two leading order corrections are significantly smaller than the leading order corrections. But this is not to say that we've done all order analysis indeed.
Okay, thanks.
Yeah, thanks for the question. Okay, now to the non-perturbative. Similar results also arise there. And the issue here is now shrinking 4 cycles because the 3 brane instantons on them are suppressed by their volumes. And you see that the smallest 4 cycle volume here is mu square over lambda. And this is precisely the same ratio as before, this ratio lambda over mu square. So really in the same vein, we learned that no obstructions arise in the first 2 regimes, at least at this order, while the third is obstructed, obviously. Also from this non-perturbative perspective. Okay, so to conclude part 1, our classification analysis manifests that the EFTs at infinite distance either decompactify or exhibit a weakly coupled tensionless critical string. And this confirms the emergent string proposal for every infinite distance limit in the Kahler moduli of 4-dimensional F theory. Obviously, the distance conjecture naturally follows because both phases come with a light tower of either a Kaluza-Klein for the compactification and a string excitation for the emergent string phase. And I must say that the emergent string had also been tested earlier in various other non-trivial string setups, however, mostly with more supersymmetries. So in the current F-theoretic setup, only with minimal SUSY, just Fourier supercharges, we are adding a very strong piece of evidence for the emergent string proposal. Okay, now in the remaining, I guess, 10 minutes or so, we will analyze the EFTs at weak coupling.
May I ask again? Sorry.
Yes, please. Yeah. Yes,
very
please.
naive question. So it seems a bit artificial, this kind of fine-tuning between the 2 parameters, lambda and mu. Do you have any mechanism that would bring you into one regime or another, or some physical argument?
So here we are just viewing them as really the moduli. So we just consider, you know, not potential to force us to some regime, but we could just go there without being obstructed by any potential, at least for this the two regimes of class 1, for example. But indeed, I mean, here I'm essentially viewing them as almost moduli, so we don't really consider the dynamics here. But yeah, with fluxes and yeah.
Has anyone tried to consider the dynamics for this kind of model?
So in principle, we can also start discussing some of the dynamics because now we have fluxes and we also have like F term and T term potentials. So we thought a little bit about this, especially in view of the third regime that is to be obstructed. But the regime we are considering is essentially not obstructed. So you can view these parts at least as really freely deformed part of the moduli.
Okay, thank you.
Yeah, thanks for the question. So now, yeah, so now to the weak gravity conjecture, and for this we are looking at the EFTs at weak gauge coupling regime. So as I said, this can be viewed as a natural continuation from part 1 because weak gauge coupling regime is a kind of infinite distance limits. So we will actually show that the Lie tower states we identified in part 1 for any infinite distance limits, they do provide a tower of sublattice amount of weak gravity particles, and that's the connection to part 1. Okay, so I guess I'm not sure if I can really discuss all of this, but let's see how much I can do. So yeah, so once again, the goal here is to find a sublattice amount of weak gravity particles at weak gauge coupling limits. So these particles, weak gravity particles, have this defining property that their charge to mass ratio is bigger than the extremal black hole ratio. So we also call them super extremal. So if you recall, the gauge coupling is inversely proportional to the volume of the 4-cycle wrapped by 7 brane. And therefore, the parameter regime of our interest corresponds to those infinite distance limits where a 4-cycle volume diverges. Now from part 1, we've learned that any limits in the Kahler moduli should fall into one of these 3 classes, 1, 2, or 3, but because we are not interested in decompactification, only 2 options remain. And now the situation gets further restricted because the shrinking 4-cycle S, the expanding 4-cycle S is not an arbitrary 4-cycle, but actually something that can support a D7 brane. And in the end, we can rule out class 2 limits as well. In other words, the shrinking 2-cycle has to be a sphere fiber, and the emergent tensionless string is now heterodyne. Also, I've claimed in part 1 that we derive the precise parametric behaviors of the Kahler parameters. And using this information for class 1 limits, we can observe that the EFT of photon and graviton asymptotes that we coupling to a dilatonic Einstein-Maxwell theory. And in here, the dilatonic coupling is computed as this particular form, e to the square root 2 times 5. So in order to address the weak gravity, we first need to check the extremal charge to mass ratio for dilatonic Rice-Nordstrom black holes in this theory. And the asymptotic EFT action, which we just derived, tells us that this mu xt is just 1. As a quick side comment, we can split this number 1 into 2 halves to separate the gravity and the dilatonic contributions. And such a split has a direct analog in the so-called repulsive force criterion for the weak gravity particles if they are present. So can we actually really claim that the spectrum contains weak gravity particles? After all, they must be light at weak coupling due to their super extremality. As you can see, this is fixed, and as you crank G down to 0, then mass should be very light. So a natural candidate to consider for the weak gravity is the excitation tower of the tensionless heterodyne string. And then 2 crucial questions remain. Firstly, can we naturally find a charged sublattice filled by the excitation spectrum? And next, are they extremal? Are they super extremal? So let's address these 2 issues in turn. Specifically, we need information on the maximal charge at a given mass level, for which a quantitative guidance is provided by the partition function of the critical hadronic string. So its expansion coefficients, these capital N's, count the states at mass level N and charge R. While a certain practical technique is available for computing them, all we need to know for our purpose is to is just the maximal charge R at a given mass level N, rather than the precise values of all these N's. So as it turns out, a general property of the string partition function already guarantees that the spectrum does contain a distinguished charge sublattice with charge R equals 2m times k. To be precise, this is the maximal charge at mass level N equals m times k squared for every integer value k. And the coarseness of this sublattice is this integer 2 times m, which is fixed by a certain topological property of the internal space. In case you're interested, the C0 here was the shrinking sphere fiber, and this S is the full cycle wrapped by the 7th ray. And the dot operation here is just to count at how many points C0 and S intersect inside X6. So the next task is then to check if these sublattice particles are indeed super extremal. And the confirmation goes as follows. So we first eliminate K to express the maximum charge R max as a function of the level N. Then by using the connection between the physics and the geometry, we derive this inequality for all the sublattice particles. So here the inequality is in fact only marginally satisfied for very large K, because this essentially comes from this inequality up here, and this boils down to N versus N minus 1, and N is very large for large K, so this is a sort of asymptotic inequality at large K. So the crucial remaining question here is the following. In this green box inequality, the prefactor on this right-hand side, which we denote as mu string, does it agree with the extremal black hole value, which is just 1? To answer this question, we start with the classical geometry. So through lines of algebras, we can indeed confirm that mu string is 1 at the classical level, at least. And the geometric intuition is that this relation is achieved by the conspiracy between various volumes and the topological intersection, if you recall this definition for this 2m. However, we've already seen in part 1, we should take account of quantum corrections, and this will change the classical volumes and may in turn correct the ratio. And the lesson from our quantum analysis is rather surprising. While the individual volumes do get corrected by quantum effects, the leading corrections at least exactly cancel in taking this particular ratio. So the deviation, capital delta here, comes only from the subleading corrections. And therefore, this delta is really suppressed at strict weak coupling, where we can ignore the subleading corrections. And here, as usual, the mu and lambda are the two large parameters governing the scalings of the two kinds. So the classical weak gravity particles still remain super extremal, even after taking into account leading corrections at least. And at this point, we might as well declare victory already. But as already asked at some point, what about the subleading corrections? What about all other corrections? So we could go slightly more ambitious and ask what happens slightly away from the strict weak coupling, where we have to also consider subleading corrections. Actually, I'm running out of time. So although I brought this story about the interpretation of these subleading effects, let me actually not talk about this and just jump to the conclusions. I mean, the story is again a victory for the subliving, but let me not give you the details of this and just conclude. So summary, so we have verified some of the quantum gravity conjectures in 4-dimensional n=1 string theory. So we have started off by addressing the emergent string conjecture for the Kahler moduli limits of F theory. In other words, we've confirmed that at infinite distance, either the theory decompactifies or a unique tensionless string emerges by analyzing both the classical and the quantum geometry of the compact internal space. The distance conjecture has then followed as a direct consequence of this phenomenon. And furthermore, the strong form of the weak gravity conjecture has also been addressed at weak coupling via the excitations of the emergent string. At strict weak coupling, the classical analysis has to be corrected by at least part of the leading alpha prime effects, but in the end, they work together very nicely to realize the weak gravity conjecture. And unfortunately, I have not managed to discuss this point, but it turns out that also slightly away from strict weak coupling, the weak gravity conjecture can be proposed. And for the this quick outlook, very quickly, so far we've exclusively focused on the limits in the Kahler moduli, which are the parameters controlling the size of the internal dimensions. This was not a restriction, at least in addressing the weak gravity conjecture at weak gauge coupling. And this was because the gauge coupling is controlled by the internal cycle volume. However, for the emergent string proposal, we have to also analyze limits in the other moduli, the so-called complex structure moduli, which control the shapes of the internal space. Now, what's even nicer about F theory is that the complex structure data govern not only the shapes of the internal space itself, but also the, so to speak, the open string sector, which is for the internal brane configurations. In fact, the limits in the closed string sector of type 2 theory had been systematically studied in the literature, but less was known about the open string sector, at least until a year ago. So having fairly well understood the Kahler limits, we started a long-term program for systematically studying the complex structure limits in F theory. And as already mentioned here, this is in pursuit of addressing the emergent string conjecture, even in the open string sector. So where are we? Initial success was made in 8-dimensional F theory, for which we successfully classified the infinite distance physics and confirmed that only these two phases may arise as predicted by the emergent string proposal. However, 8DF theory is highly constrained by a lot of supersymmetry. It's got 16 real supercharges. So the evidence here may not be considered too strong. So I'm now looking into 6-dimensional EFTs of F theory as the next stage, together with Timo and his student Raphael. And we are finding a lot of exciting novel features, but so far, everything is consistent with the emergent string proposal. So hopefully in the near future, I will be able to give a stronger statement on this and also to provide clean intuitions behind this from the geometry of string theory. And that's where I wanted to stop. Thank you very much.
Thank you very much for this very interesting talk. Are there further questions? Yeah, maybe I have another question. So in part 1, you discussed all these limits in a very general setting. So can you realize, do you have examples of concrete, like say string compactifications or like Calabi-Yau or something that exhibit these types of limits?
Sorry, you mean the classification of the Kahler limits? Yeah.
So do you have examples with these types of limits?
Yeah, so we do have examples actually written in the paper, but yeah, so here I have not brought any examples, so this may look very abstract, but in fact, this graph I drew for the weak gravity conjecture part, for example, was from a concrete example. I didn't bring the geometry actually here, but yeah, but there are examples. I mean, we can construct U1 models systematically in F-theory in terms of some, multiple sections, as you may know. So, first of all, we need to engineer, at least in the weak gravity part, you need to engineer some U1s, and then there is a way of constructing it systematically, and then we produced a lot of examples for that. But that's for the weak gravity part, and for the emergent, the distance part, you can just consider lots of Kahler limits. I have not also written down any of the concrete expressions for the parametric forms, but the forms that have been all classified, it's all written in the paper. I just didn't bring it in order not to bother the audience, but yeah, it's all there very concretely. Yes.
Okay, thanks a lot. Any final questions?
Yeah, I have probably another stupid and
yes, please.
But so actually in this work in progress, do you have better control of the quantum corrections? Normally,
good question.
The Kahler model, the complex structures is more constrained, and you have better control of quantum corrections for it, right? At least for the closed string, as far as I know. So I was just wondering whether there is more hope of having analytic control on this.
You mean complete analytic control?
Yeah.
Oh, okay, I haven't actually thought about it. So actually, even at the classical level, so as I said, the starting point, the initial success was in 8 dimensions, where we had like 16 supercharges. So you don't care about the quantum corrections there. And the thing I'm looking at for now is actually 6-dimensional EFTs with 8 supercharges. Again, you don't care about the quantum corrections. Actually, once you get to 4 supercharged theories, then you will start considering all these corrections seriously. But I must say, I'm already stuck with the, I mean, not stuck, but I'm already struggling with the classical analysis in theories with 8 supercharges. So, I mean, your question must be asked very seriously, at least when I get to theories with 4 supercharges in the complex structure side as well. But actually, the complex structure analysis turns out to be much more non-trivial than the Kahler side, even for classical geometry. So we are actually, one at a time. We are starting with the classical geometry at this point.
Thanks.
Yeah, thanks for the question. I mean, quantum corrections are very important, as you say. It would be really nice to have a full control of the quantum corrections analytically, but yeah, it's difficult with just n equal 1 supersymmetry.
All right, I think all questions have been answered. So thank you very much, Seung-Joo, for this very interesting talk and this very interesting overview on the Swampland. And we hope that at some point we can welcome you on the Southern Hemisphere in person.
Thank you, that'd be great.